Hallo, it's dumplet here. Here's an item on number theory. Find all pairs of natural numbers m and x such that m raised to x plus x is equal to m squared plus x squared. Credits to the Art of Problem Solving community for this item. As usual, pause this video if you'd like to give this item a try, but if you're done, let us dive into the solution. Now, just by taking a look at the given diophantine equation, it's actually pretty weird. And it's this term over here, the m raised to x, that makes things very interesting, because m and x are variables in the question, and that's going to suggest that, well, because x is in the power, x can't be that big. And because m is in the base, m can't be that big as well. So, for example, let's just try to, I'm going to write this a little bit differently for now. I'm going to write it as m raised to x minus m squared, and I'm going to write it equal to x squared minus x. And let's just try to make, for example, m constant for now. So if m is constant, let's just say, I'm just going to show you for 3, for example. So 3 raised to x minus 9, that's going to be equal to x squared minus x. So, well, I'm technically comparing something that is exponential. So the 3 raised to x minus 9 is an exponential function with something that's quadratic. So as x grows bigger, the left side is going to be greater than the right side. Again, eventually. Okay, so if x is big enough. So if m is a constant, x can't be that big. So that's going to tell us, okay, x can't be that big. All right. Now, on the other hand, let's try to fix a value of x. Let's just fix x to be constant. So let's just say if x is a constant, let's just say x is like 5, right? M raised to 5 minus m squared, that's going to be equal to a constant, 5 squared minus 5, so that's 20 in this case. And take a look here. Because this was previously the x, again, the x can't be that big, or m can't be that big either, because, well, I'm raising, for example, if x was 5, then I'm going to raise m to be 5. So it's going to get big real quick. So m and x, they both can't be that big. So maybe we want to try for small values of m, and then after some point, we should be able to see that, okay, that's going to be too big of a value, we should stop. So that's going to be the idea behind the question. So, I mean, there's no immediate observations we could have from this except to just kind of try some values out. So I'm going to copy this one, and I'm going to start with doing some trial and error on the values of m. Now, I guess one obvious value is going to do m equals 1, because m equals 1 is going to give 1 raised to x minus 1 squared. That's 1 minus 1, so 0. So 0 is going to be equal to x squared minus x. That's going to give me x times x minus 1 is equal to 0. Again, just take the positive root because we want natural number solutions. And that's going to give me the solution of 1, 1. That's good. So that's for m equals 1. And let's just try m equals 2, for example. If m equals 2, we're going to have a 2 raised to x minus 4. That's going to be equal to x squared minus x. Now, again, it might not be obvious, but a bit of trial and error is you're going to get x equals 4 to be a solution. So x equals 4 is going to work. Now, I'm particularly interested in letting x to be a kind of a bigger number. Now, because I know that the left-hand side is going to be exponential, it's going to have exponential growth. The right side is just quadratic. So let's just try to see if x is greater than 4. Let's just try to see how it's going to grow. Because, well, let's try to compare the 2 raised to x and then x squared term. In fact, you guys can prove it by induction that it's going to be 2 raised to x is going to be greater than x squared for x greater than 4. Well, again, it might be pretty obvious because we're comparing a quadratic and an exponential. So the exponential function is going to grow exponentially. It's going to go fast. It's going to grow faster as x becomes big enough. And, well, I could kind of see that I could rewrite this actually as 2 raised to x plus x is equal to x squared plus 4. And I could just kind of use the addition property of inequalities, and I'm going to add these two equations. So 2 raised to x plus x, it's going to be actually greater than x squared plus 4. So equality is actually impossible for x greater than 4. Okay, So if m equals 2, x can't be greater than 4. So I believe, well, x equals 4 is going to be this only solution. You could try x equals 1, 2, 3, but those are not going to work. So at least for m equals 2, I'm getting this solution, 2, 4. All right, nothing obvious yet for what the upper bound for m is, but at least for m equals 2, there's an upper bound for x actually. X could only be at most 4. So all right, I'm just going to do this part again. So m raised to x minus m squared is x squared minus x. Now let's just try m equals 3, the next possible value. Again, there isn't really immediately nice observations. That's why I'm just kind of doing some trial and error. Now, I mean, I can expect that there's going to be an upper bound eventually because I know m and x can't be that big. But so far, I'm just going to try to see whatever I can get. So I might want to try to see what are the solutions to this. Okay. Right, nothing immediately obvious. Let's just try to have some values. Now, x equals 1, it's not going to work. X equals 2 is not going to work. Right, x equals 2, I'm just going to kind of compare. X equals 2, the left-hand side is going to be 0. Right-hand side is going to be 2. Okay, so for x equals 1, it's going to be negative 6 and 0. And then for x equals 3, the left-hand side is it's 18. And then the right-hand side is going to be a 6. Now, take a look here. At x equals 3, the left-hand side overtakes the right-hand side. And because it's exponential, we expect it to grow, actually. You guys could try x equals 4. You can see if x equals 4, I'm comparing 72 and 12. And because of how the exponential function grows faster, again, you guys could prove this via induction, or you guys could just use this logic that, okay, at m equals 3, x equals 4, at m equals 3, x equals 3 is where the left-hand side overtakes the right-hand side. So there's not going to be a possible value already, a possible solution for m equals 3. And that's something interesting because maybe it's going to be true for all the other possible values as well. Now, let me just try to substitute, maybe instead of doing some trial and error for m, I'm going to try to substitute values of x now because, well, at least for m equals 3, x equals 3 seems to be the place where it's going to overtake. So let's try to do some trial and error on x now. I haven't done trial and error on x technically. All this time I've been doing some trial and error on m. So let's try to consider this one, and instead of considering for m, I'm going to consider x. So if x equals 1, I'm going to have m minus m squared is equal to 0, and that's pretty much how we got the 1, 1 solution, so I'm just going to leave that to you guys. If x equals 2, I'm going to get 0 is equal to 2 squared minus 2. That's a contradiction, so that's not going to work as well. If m equals 3, so I'll have m cubed minus m squared. That's going to be equal to 6. And well, we could just do some trial and error for m. It's not really a difficult equation to solve. All right. If m is equal to 1, okay, that's going to be 0 here. So that's going to give 0 on the left-hand side. If m equals 2, that's going to give me 4, right? Not quite. If m equals 3, that's going to give me 18. All right. I think it's not going to work because, well, the left-hand side, all right, this equation, it's actually an increasing function. So it's not going to work in this case. So, okay, apparently for x equals 3, it's not going to be possible. Okay, so, right, just continuing on. X equals 4 case, so m raised to x minus m squared is x squared minus x. For the x equals 4 case, m to the 4th minus m squared, that's going to be equal to 12. All right, we could try to do some similar reasoning. So m equals 1, that's going to give 0, that's going to be too small. M equals 2 is going to give me, all right, actually it's going to be correct actually. M equals 2 is going to give me 12. And I think, yeah, we already got the solution 2, 4. That's how we got the 2, 4. And then Let's just try if m equals 3. I believe it's going to be too big. If m equals 3, yep, it's going to be too big. It's going to be 72. And you guys could expect that because this is an increasing function, if you increase the value of m, we're not going to get solutions. All right, so finally, let's try x equals 5. Oh, a bit of a spoiler. I said finally. But let's just try to see x equals 5. So m raised to 5 minus m squared, that's going to be equal to 20. Okay. M equals 2. It's going to give me 32 minus, okay, that's going to be 28. That's already big. Now, m equals 1. That's obviously going to give x to be 1, as mentioned. So I'm just going to start with m equals 2 now. And just at x equals 5, m equals 2, it's going to give me something that's already bigger than the right-hand side. And because the left-hand side, it's going to grow faster than the right-hand side, although this is not really a rigorous proof, we could try to see that x equals 5 is already too big. So what more if x equals 6, x equals 7, x equals 8, and so on. It's going to be pretty much it. Now, this solution does require a little bit of rigor, so I'll just leave that to you guys. But the basic idea is there. We just have to make sure that observations, the bounding, getting the upper bound to these diophantine equation is the crucial part. So we're actually done. We did some trial and error in m and x, and we reached a point where, okay, stuff is too big. There's no point in trial and erroring other possible values anymore. So we got two answers, 1, 1, and 2, 4. And in fact, these two are the only solutions. Now, if you guys want to write a more complete solution, try to put them in the comment section below, and let's try to compare our solutions. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye.